All right. So we are recording. Let me hand over the floor to group 623T so they can present their single winged heliostat.
All right, perfect. Just to clarify, you guys can see my screen. My little thing went away.
We can, yes.
Okay, perfect. So I guess I'll get it going. Thank you guys for joining us this morning. We're group 623T. My name is Caden Bauer. We're going to be presenting our single winged heliostat that we've been working on all semester. We're super proud of it. So let's give you guys a quick intro on our team. We like to call ourselves a Weenie Hut Junior Incorporated. Kind of came up in the beginning of the semester, that's kind of what we went with. I'll just go through our team. It's me, myself, Caden. We got my peers, Daniel, Carl, Raul, Rodolfo, Samantha, and Steven. And kind of going through what we kept going back to throughout this semester, throughout our design, was a low cost. We understand the main purpose of this project was to bring the price of solar power and thermal power down. So that's kind of what we wanted to keep with. But keeping that in mind, we also wanted to create a product that was functional and scalable for the real world applications. We wanted to keep it with the accuracy that our metrics asked for. We wanted to make it very easily to source and assemble, just in case anything does break in the field. Someone can go in and repair it super quick. For our purposes, we use a lot of 3D printed parts just for the nature of this course. These parts can be changed out with injection molded parts and other materials as it is scaled up. Going into our actual design, this is what it looks like. It says dual winged heliostat. We'll kind of get into that later. We had to make a couple design changes last minute. I went from a dual wing to a single wing. But our reflector backing, starting from the top going down, reflector backing, it had a 345 square centimeter reflection area. The top actuation assembly was powered by a gear drive with a 1:2 ratio. We're able to step it down and achieve a 0.11 degree accuracy in the elevation direction. The bottom actuation assembly, however, we didn't gear it down quite as much, so it could only achieve a 0.45 degree level of accuracy. Both of these were within our metrics, so it was still achievable. And the basic controls we like to hold at in what we like to call the black box. They kind of hold all of our electronics, bits and pieces, the power supply, the ESP32, a couple motor drivers, and then the temperature sensor as well. Some key product specifications that we had throughout our project is it can rotate both an azimuth and elevation axes. During our laser test, we were able to hit targets within the 0.5 degree accuracy, as I mentioned earlier. Throughout the semester, for all of the testing, we're required to clip in our design into a standardized, kind of like a tripod camera mount. So our design is able to do that. It was able to withstand all the winds that we were put up to, including an 82 meter per second wind. That is commonly seen as the highest wind speed out in Las Vegas, where these were looked at being in use. Almost all of the parts are 3D printed besides our electronics and our hardware, obviously. So it's very prototypable and easy to assemble. One of the biggest things is everything in our design is covered. Kind of protects it from the environment, the wind, the rain, the dust, everything like that. It won't be able to get into our design. And then all of our software and coding is written through Arduino and kind of C++ code. So it's easy to use and easy to understand. Now I'm going to pass it off to Raul, and he's going to kind of go through each of our subsystems and how they work in a little bit more detail.
Hi guys, I'm Raul Lopez. So I'll be talking about all the exploded CAD views. So we'll be going one by one through each subassembly. So starting off, we are looking at the reflector subassembly. So in green, we have our reflector backing. So this is what's going to allow for the reflector to actually mount to. So the reflector uses adhesive. So we'll be able to basically just kind of stick it to the reflector backing. This reflector backing is then connected to the reflector arm denoted in blue. And this is held together by just a single pin. It's basically press fitted, so easily to take in, to put in and take out. Then the reflector arm is then connected to the central elevation bar, which is then held together in by another pin. So basically, this whole subassembly is 3D printed, which makes it really quick for manufacturing. Reflective surface can be easily cleaned since it's basically just only the only part you'll be seeing is just reflector and then stuck to the reflective backing. Easy scale to any size, and then really only utilizes a total of 4 pins to be held together. Next slide, please. And next, we're looking at our top assembly. So starting from the bottom and going up, we have in orange, this is going to be our top flange. So our top flange is, main priority is to be holding in the motor that will be controlling and driving the elevation bar. So the motor is going to be held in by 4 M3 fasteners, which then we have our first gear, which is going to be our motor gear that's connected to the motor shaft. This then we have a riser ring that's attached, that's inserted into the flange, which then we have our top tube, which is denoted right in the center. It goes over all those components. And next we have our elevation bar that's going to be going through these slots in the top tube, which we also have our second gear, which is our elevation gear that's attached to the elevation bar. And this is held into to the elevation bar by another pin. So using a lot of pins here, very easy to print, very easy to take to put in, take out. And as well, we have our top cap, which is going to be housing our limit switch, which is held in by another 2 pins. And for actuation of that limit switch, we are deriving our, I guess you would say, motivation from a camshaft. So we have a sort of hump that's on the elevation gear, which is then helpful in order to actuate the limit switch. So as it turns around, the hump is going to make contact with the limit switch, press it up, and that's what's going to be helping for our homing and also stopping the elevation bar from rotating it even anymore. The gear design that we have is a 1-to-2 gear ratio, which makes it very helpful in terms of accuracy, and then also utilizing microstepping as well for improved accuracy. And this all contains a lot of safety features here to prevent any further damages. Next slide, please. So for our next assembly, we're looking at our bottom subassembly. So starting from the bottom and going up, we have our base box, which has cooling vents as well to keep from all the any control components, electrical components from heating up. So this and that includes the power supply, and then also the breadboard, which houses all of our wiring for Arduino. So then we have our lid, which is then just placed over the base box. It's press fitted in, so very easy to take apart. And with that, we have our motor mount, which is then attached to the lid, utilizing M5 fasteners and nuts, screws and nuts. And for our motor mount, it's pretty easy to see. It's going to be mounting our motor, which is then used by another 4 M3 screws. And this motor, the motor shaft, is going to be attached to a motor hub, which is held in by a set screw that will keep the motor hub from coming off of the motor shaft. So this motor hub is then fastened to our bottom tube, which is then held together by M10 screws and utilizing washers as well for just better contact of the fasteners. And then on top of that, we have our bottom flange, which is utilized to basically connect the bottom assembly to the top assembly. And from all this, it's majority is 3D printed, minus the control components, motor, and fasteners. We'll go to the next slide here. All right, and so we have all of our sub-assemblies kind of distinguished one by one. So we have our top, we have our reflector assembly, which is then connected to our top assembly. And this is mainly to drive our elevation. And then our top assembly is then mounted to the bottom assembly, which the bottom assembly is majority, it's mainly, its main priority is the azimuth. So reiterating this, majority of all of these components are 3D printed, which is it makes it easier to source and also helps with cost. Parts are easily replaced as well, very scalable, And because it's all 3D printed, it makes it extremely cost effective. And then the actuation is split by 2 axes of rotation. And that is everything for the exploded views. And now I'm going to give it to Stephen, who will then explain our wind survivability test.
Hello, my name is Stephen, and I'm here to talk about the 2 tests that we did to test the viability of our design to meet the design requirements for the conditions of Las Vegas and being able to hit the laser tests. So our first test was the wind survivability test. That was to show the endurance of our design in high winds, as well as to represent the environmental conditions that could knock over and destabilize the design, causing it to fall over or just fail to hit the target. Even though this image shown is from our previous design during the wind test, as you can see, it has the 2 reflectors on the side with the longer elevation bar. We determined that our current design was better for a wind test since it has less surface area, causing less wind force to destabilize the design during actually accuracy hitting. I want to play the video really quickly, kid. You can see it's moving. All right, if you want to go to the next slide. For our second test we had to pass, we had a laser reflection targeting test. This test was meant to show the accuracy of the laser hitting the targets, but as we saw through iterative testing, we also had to hit the targets with precision in order to hit it during our actual testing. For our final test, we actually hit the targets within a 1.5 degree accuracy. We hit that 1.5 degree accuracy because of the lack of consistency of our azimuth being direct driven on a motor hub. But on the other hand, our elevation was precise, and we were able to develop a method to eliminate the backlash of the gears by zeroing at a horizontal. And as well as using 8th step microstepping, we were able to get within the 0.11 degrees every single time. And here are videos of our laser test. You can see it homing in on the targets and hitting them. And I'll pass it off to Carl to show our design evolution throughout the semester.
Right, hello, I'm Carl Jacino Ortiz, and I'm going to be showing you the design evolution of this product. Me and Sammy actually worked on this design back in the last semester in Mech 2. So we're pretty familiar with this design, and we decided to iterate on it because it was what we worked on before, and we were quite happy with what the design, was able to do. So we decided to just, try and make it real this time instead of just designing it conceptually. So in the beginning, we basically had the dual wing heliostat design, and the base was significantly different because it was designed to be buried into the ground so that the entire module would not move. But then as we got into the prototyping phase, because we were now designing this product so that we would put it onto a standardized mount, the base was significantly changed. There were also issues with the central column. We basically had to change that quite a bit too, as well as separating some elements inside of it. And then we also had to go with 2 reflectors instead of 4 because it just made for a more simplistic design. And it also made it so that moving the reflectors up and down was more consistent. The final product had a very significant change going from a dual wing to a single wing, because even with the change, instead of going from 4 reflectors to 2, it still had a lot of inertia, which made it so that making the reflectors go up and down was actually very difficult and kind of inconsistent. So that had to be changed significantly, which is why it went from a dual wing to a single wing design. Next slide. The base was redesigned quite a bit so that it could be mounted on a standard mount. The system that was shown in the previous design was made of PVC piping. We decided to swap to just making a 3D printed box because it's easier to produce, it's faster, it's less costly, and it's much simpler in general. Just the design is much quicker and simpler. and the base really just exists mostly just to keep our electronics in one place. And due to us having all the electronics into the base, cooling vents were added so that they wouldn't overheat and that they wouldn't be damaged during operation. Next slide. Now, the central column was changed quite significantly due to the previous design relying on a belt drive to operate the crossbar. That was very costly. It was also very finicky because you'd have to have a very, specifically tailor-made belt drive, and it would also be very finicky as a design. So that was changed quite significantly to basically take the elevation motor and the azimuth motor and essentially separate those two into more defined separate systems, which is where we came up with the idea of having the bottom assembly and the top assembly connected with the flange, so that it was much easier to essentially just take the two sub-assemblies, design them or construct them, and then essentially just put them together. It makes the construction much easier. And also the top assembly was changed. Instead of going from a belt drive, we did direct drive. Makes things simpler, easier, quicker. It just makes the design less complicated in general. And we also have 3D printed gears. The central column used to be PVC. It is now 3D printed material. The same thing with the bottom section as well. And we also don't have a worm gear anymore. So everything's pretty much just direct driven at this point. And then I'll hand this off to Sammy or Samantha.
All right, so for our reflector model, as we were previously talking about in our design from last semester, we had 4 reflectors on there and it was a dual winged model. So to make it simpler, we went down to just 1 reflector. It was easier for our laser test and honing in. So with our new reflectors, we just put it on there. There's a sticky adhesive on the back of the mirrors. So you just put it on there and it's good. And maintenance is really easy with that. As before, we had snap fits with our original design. So taking it in and out was a little bit harder. So I think this just simplifies it. And it also reduces the number of parts and cost and the wind resistance. So if we go to the next slide. For our limit switches, we previously talked about this, but we wanted to give a closer picture of it. So on the left, we have our elevation. So our limit switch is going to be at the top in the actual cap of our design. So our gears have a camshaft design to them. So as it rotates with the elevation, it will stop the actuation once it hits the limit switch. And then on the right for the azimuth, so this is part of the bottom assembly. There's actually a set screw on the side, as you can see, the fastener for contact arrow. So that has a dual purpose. It both holds the motor hub in place and also works to make contact with the limit switch to stop the azimuth actuation. So if we go to the next slide. So as I was previously talking about wind speed and wind force, with our current design, we have our area over on the left. We used a max wind speed of 82 miles an hour because that's what we researched. It's what we found when we looked up wind speeds in the desert. Our wind force was about 110 newtons, which gave us a stress significantly less than the yield strength of our PETG plastic. With our previous model for our dual winged from last semester, our wind speed we used for 82 miles an hour, our wind force came to about 300 newtons and our stress was tripled as a result of that, but still fit within the design criteria and having a factor of safety greater than 2. I'm going to pass it off to Rodolfo, who's going to talk about angle calculations.
Hi, I'm Rodolfo, and as Sammy said, I'll quickly cover how we calculate our azimuth and elevation angles. So first, we should understand the nature of the experimental setup. The setup was that we had a scaffold overhead of the center of the mirror, and the scaffold would hold a vertical laser. So with the heliostat module then being placed on a corner of a table, we would command it to rotate azimuthally and elevation wise. Using the equations shown on the right side of the page, we were able to calculate the azimuth and elevation angles based off a given ABC or a wall target. And then similarly, if we were to do a little bit of manipulation, we were able to obtain the ABC coordinates with if we were to spot our module on a target on the wall. So next I'll be passing it over to Daniel, who will cover some of the cost breakdowns.
Awesome. Hi, I'm Daniel. I'm going to give a brief overview of the cost. So the total cost for one prototype of our unit is about $175. And this is the combined design cost as well as the given parts cost. And the given part cost is from what the MEC3 teaching team gave us. That included the ESP32 board, stepper motors, limit switches, mirrors, and power supply. And the design cost is what we manufactured this semester on our own. And that was only accounted for 40% of that total $175. For the total design of the heliostat, it's broken down into 60% cost is for the electrical components, 26% is for 3D printed parts, and 13% is for the mechanical components, which includes fasteners and off-the-shelf components. And for a thermal farm of 3,000 heliostats, the total cost would be approximately $446,000 with an assumed 15% bulk discount. Next slide. And why, just to sum up why design should be selected. It's low cost, simple design. We have individual actuation for each axis. It's also easy to manufacture because more than a quarter of the heliostat is 3D printed. And finally, it's scalable, high stability, and has a factor of safety much greater than 2. And with that, we want to thank you for your time and want to offer this moment for any questions.
All right.
Hey guys, this is Tom Singer from Northrop Grumman. I'm curious, is this the product that you would intend to be installed in Las Vegas in an array of 3,000 of these?
Yeah, I'll take this one. We are, the only change I think that we would make with this design is we would add more of a gear ratio to the azimuth kind of rotation to get a little bit more torque. And that way we would be able to scale up our design a little bit more. But yeah, this would be a product.
So when you say scale up your design, what are you referring to?
Basically increase mirror size to actually increase the effective thermal output of the system. Because currently with the go ahead.
So if you're talking about scaling up the mirror size, why are you quoting what it would cost to install 3,000 of these, which is essentially a prototype intended to investigate the mechanism, right? You said, hey, it'll cost $440,000 or whatever it is to install a farm of 3,000 of these, but that's not really relevant, is it?
If I could jump in, sorry, they're doing that artificially because I asked them to as part of the report.
Okay.
So sorry. Yeah, that's on
all right.
me.
So like a lot of my sort of concerns are focused on the fact that, you know, you're showing a stress analysis, right? And you said, well, if we have to survive 82-mile-an-hour winds, you know, what loading does that put on our system? Well, that loading is going to be highly dependent on the size of your mirror, right? That's what's going to catch most of the wing, right? So if you're talking about you have to scale up the size of the mirror, well, that's going to radically change the results of your structural analysis, right? It's going to radically change whether your pins are going to be able to provide sufficient torque or sufficient resistance to resist the torque of wind acting on mirrors. So a lot of what you've done here in terms of like testing out your mechanism, I think is good. I really don't know what we're doing with the wind test. I really don't know what we're doing with the structural analysis. think that a lot of the changes that you made to the basic design of going from what was previously a dual wing design to a single wing design, if that's a change that was just for the prototype, like how does that affect the mechanism? Like, would you be using the same mechanism or similar mechanism? And what have you tested that's applicable to the real world final product?
Okay, yeah, so we did do testing on that original design. It was hard because we had to wait for a bunch of parts to be manufactured through the class, and it just wasn't feasible with the 3D printer that we had. So we had to alter our design a little bit just so we could prototype and actually get some testing out, which is why we switched it to the single wing heliostat. But we're confident with the previous design as well to make it the dual wing heliostat that we previously mentioned.
Okay. And then the other question I had was you were showing accuracy figures of 1.5 degree on your pointing, which doesn't meet the customer requirements.
Yeah.
But then you said, well, we can get that down to 0.1 degrees. What is that based on? Have you proven that out?
Yeah, so when we did our initial testing and we initially calibrated, we were getting those accuracy values. The one that was 1.5 degrees, they gave us coordinates, and we had to basically feed those coordinates into our calibration system. So I think those issues lied a little bit more with our calibration system more than it did with our heliostat accuracy as a whole, which we're still working to flush out.
Have you achieved 0.11 degree?
0.11 degree, not with the testing we've done currently. We would have to finish a little bit more with the code.
Yeah, that was basically the resolution we could achieve on the elevation stepper motor the gear train on the top.
Well, I mean, just from like basic geometry, I don't think the accuracy of pointing your mirror is exactly the same as the accuracy of directing a beam towards a target. I think you're going to find that the error in that will be twice the pointing accuracy, or error rather.
Based off
if your mirror,
yeah,
if your mirror moves by 1
normal.
degree, the reflected beam is going to move by 2 degrees.
By 2
right?
degrees, yes.
Yeah,
yes.
so it's going to be double that. So, you know, I don't think your customer cares so much about where your mirror points as much as where the
laser
beam
goes.
is being reflected to.
That is a good point. We'll get back together as a team and focus on that for our final report that we submit. That is a good point. Thank you.
So I have a question. If y'all wouldn't mind going back to your cost slides real quick.
Yeah.
I think it's, yeah, right there. Okay. So the first thing, it wasn't on this, it was on the other one. You were saying that this is scalable, and you're saying that that is in reference to changing the size of the mirror?
And all of our parts, because they're easily 3D printable and hopefully in the future injection molded. Yeah, so the only thing that would really be changing the cost would be the mirror size, yes.
Okay. You want to be very, very careful when you use the word scalable, because as a business person, I hear the word scalable and I'm like, oh, good, they can make 1,000 bajillion of these and take it to market. That's what
Okay.
scalable means in the business world. It means you can scale up production to produce 3,000 of them very quickly and very easily. So just be very, very careful with that word, because scalable means a lot of different things to a lot of different people. My second question was, okay, so you have your costs in here, and I see design costs and I see given parts cost. Who's making these parts?
So the design costs, these parts were 3D printed by us inside the lab. The mechanical portion, like the hardware, these were off-the-shelf parts that we ordered from third-party vendors such as McMaster. The given parts cost, these are just provided to us by the teaching staff. So these are like NEMA motors that you could probably get off anywhere online. The stepper drivers, a lot of these other websites, but they're pretty they're off-the-shelf parts.
So who's putting the heliostat together?
These would be done by people on site. We haven't completely figured out the manufacturing cost, but based off our experience from last semester,
Mhm.
doing the charts to figure out the actual assembly and manufacturing costs. In
Do you see where I'm
reference,
going here with this
yeah,
questions? Yeah. This is
So-
not your actual cost, because
no,
from what I'm hearing is you're 3D printing it. Well, if you're working for free, I have got a lot of work I need done over here. And if you're working for free, please come talk to me.
Yeah.
So that's kind of the first thing you really need to consider. I know everybody's like, oh, we're printing them off ourselves, but and for you to do the prototype, you're not going to charge because you're doing a prototype.
Yeah.
But if you're doing 3,000 of these for a thermal farm, you need to pay yourself, or you need to pay the people who are printing the parts. Then you got to pay the people putting it together. So this total cost is not accurate. It's very deceptive because I see no labor costs in there. And let me tell you, if you go look at, costs for people, labor costs in any company are usually some of your highest.
Okay,
So,
we were going based off of
yeah.
our experience from MEC 2 when we did
Mhm.
the charts and the stuff that we were given in MEC 2 for
Right.
the total time
But
and
that's what I'm
cost to
saying.
do
You
it.
think more,
Okay,
expand.
okay.
Okay. But other than
Okay,
that,
yeah.
very good. But yeah, be very careful of
Okay, thank you.
scalable and labor costs. That's all I
Okay,
got.
perfect.
Other than that, for the little bit of engineering stuff that I understood, looks very good.
Thank you.
Could you please change to page 17? Yeah. So for the structure analysis, in addition to what Tom just commented, the size of mirror will change the loading condition a lot, and will change the stress analysis a lot. There is another thing that I'm just curious. I'm not saying that you're wrong or anything. So the stress analysis here you're doing is for the what is called the vertical thing, right?
It'd be for our safety position, yes.
Yeah,
Operating wind speed would be. Oh, take it ahead, Samantha.
Okay, so for this, this isn't the greatest image for it. But basically, so for this analysis, our wing would be at a 90-degree, so just completely vertical. So that's what the calculation is based off of.
Yeah, so I based on what your picture shows here, you have the Y. So I'm thinking your stress analysis is for this cylinder. But when I look at this picture, I'm kind of feel that probably the part that connecting the mirror, the joint that rotate, that part will fail first before the cylinder itself. That's what my guessing, but at least you can check both which part is actually the critical point of your structure, and then see which one will fail first.
Yeah, no, it's definitely a good point. No, definitely since we have this new design, it's been a little bit difficult because it's just been so rushed towards the end, but no, that's a really good point.
Yeah,
I'll
because
definitely look into that.
Yeah, if you look at it, it's like the cylinder, my English is not good. I don't know what is that called, but that thing, the cylinder thing, it looks much stronger than the rotating joint that is holding the mirror. Is right.
Yeah,
So,
no, you make a great point.
Yeah. So you probably can check that one. And on page 20. So why the design should be selected, and it said the safety factor is much greater than 2. What is safety factor about? It's like
so I've done bending and shear stress calculations for the design, and our factor of safety was even over 100. So
yeah,
that's what that's based off of.
So my personal opinion is that safety factor is not the higher the better. If the requirement, let's say, I don't know what the requirement, but if the requirement is 2 and you are about 100, it probably means that you can optimize your design better,
Okay.
right? So just my personal opinion. And overall, great job. Thank you.
Oh yeah. No, thank you for your points.
Okay, any other questions from the panel?
Not necessarily a question, but a comment that thank you guys for all having the same background on your Zoom. I know that's something small, but it does make you feel more cohesive as a team from the panelist viewpoint. So it makes it look like you have it slightly together, you know, so you kind of know what you're doing. So remember, little teeny things like that seem crazy, but they do make an impression. So thank you for doing that.
Thank you.
Thanks.
Okay. Anything else anyone wants to say or ask?
Yeah, so this is Rick Miles with Northrop Grumman. Just got a quick thing. You made a mention when you were talking about 3D printing because you were replacing PVC with 3D printing. Just understand that you made a comment, I think, that it was cheaper. 3D printing can be quite expensive. And I know you're talking about moving to injection molding, but injection molding is probably not cheaper than purchasing PVC pipe off the shelf. So just make sure you're comparing apples to apples.
Okay, yeah, that's something we'll consider. Thank you.
I guess it's also very dependent on also time constraint as well as the filament that we're using. So a lot of this is used utilizing PETG. So I can't remember the cost of. Kane, do you remember the cost of what PETG was?
I do not, but I think he's talking more about the just time it takes in overall to print all these parts as opposed to just ordering.
Yeah,
No,
because labor
massive
costs would come into effect with that.
Yeah, true. You're working for free, man.
Yeah. Is there any other questions, comments, concerns? If not, Dr. Traum, thank you guys again. Is there anything you would like to add, Dr. Traum, to kind of wrap all this up? I don't know what you have to do from a panelist perspective.
No, I think if there are no more questions, we can wrap it up there. Let me stop recording here.